All right, good afternoon, everyone. Just wanted to post a demo of calculating confidence intervals around effect sizes. We didn't get a chance to go through examples of this in class, and having you do these on this assignment that's due on Friday, so just wanted to go through and walk through just a demo of some of these using some of the data that we've used previously for independent samples T, paired sample T, and single sample T. So examples that we're going through just to clarify, if we go through, as you're walking through, want to link this back to stuff that we've already done in class. Make sure to go through and pull up your single sample T, that handout that we gave there. Here we're looking at comparing PTSD, the CAPS total scores from our data set versus some normative stuff, if you recall. The independent sample T that we're going to do is taken from this handout. We're looking at marital satisfaction across men and women exposed to motor vehicle accident trauma. So again, and then the example that we're going to be using for the paired sample case is this handout that we had gone through when we were doing the paired sample T, looking at pre- to post-treatment differences in cold, distant interpersonal styles. So does inpatient treatment sort of address sort of this cold, distant interpersonal style? So these are handouts that you already have. These are just examples that we're going to pull from when we're going through calculating the effect size and then the confidence interval around that effect size. So have those up if you want to go through and get a good look at where some of these data are coming from. So going back through, remember that for calculating our confidence intervals around effect size, our effect sizes aren't distributed on normal central T distribution. We have a non-central T that we're going to need to use in order to calculate our confidence intervals on effect. This is where Steiger's non-central distribution for interval estimation, this tool, we had the link. That's where this is going to become helpful, because what we need to do, remember, so once we calculate our effect size, we're good, we have our point estimate, but in order to calculate the confidence interval around that effect size, what we need to do is we need to enter our test statistics in order to get an upper and lower limit for the non-centrality parameter, and then that's what we're going to go back through and back translate into confidence intervals around our effect. So we had talked about our non-central T distribution, some of the characteristics of that here. Recall that sort of getting our exact mathematical calculation of exact non-centrality parameters is kind of difficult, but this tool by Steiger, fantastic. Here's the link. Make sure that you go down through and get that. Some people have mentioned that they're having difficulty getting that on Macintosh. I don't know if this works on Apple, but it does work on PCs, so either download it to a lab computer or something like that so you can go through and get this. So. And here's the tool right here that we're going to be using in the demonstration. So remember that calculating confidence intervals for effect size is basically just a matter of taking the non-centrality parameter, or the lower and upper bounds for the non-centrality parameter, and just back translating that into effect size. So for our single sample T, we're just taking our non-centrality parameter divided by the square root of the sample size, gets us our lower bound, upper bound. Same thing for our independent samples test. Take our non-centrality parameter, multiply it by the square root of the reciprocal of the sample 1 size, cell 2 size to get that. And then for our repeated measures, same thing. Basically, we're just running a single sample T test. Looking at the mean difference is whether or not that's different than 0. So for a repeated measures design, we're going to go through and use the same process as we did for our single samples. Only thing to remember here is that because our test statistic for our paired sample test is using the standard deviation of the difference scores in order to calculate our test statistic, if you want to calculate a confidence interval around an effect size for repeated measures or a paired sample t-test, the point estimate for D that you need to use is the mean of the difference score over the standard deviation of the difference score. Now, we had talked about pros and cons of standardizing your effect using the standard deviation of the difference score, but this is what we need to do if we want to calculate a confidence interval around that. So just take those things into account. All right. So for our first effect size here, what we've done, and again, I pulled this from our single sample, the in-class demonstration that we used for the single sample t-test. What we're doing in this hypothetical is saying that we have 27 individuals who we've identified as having PTSD following a motor vehicle accident. We've scored this using a interview measure. And so what we want to do is see whether or not our scores for this motor vehicle accident sample with PTSD, how our total scores on this interview measure stack up to, say, some known reference value for a large sample of accident survivors. Okay, so we've got our score, our participants, number of participants. We've got 27 people. We have 62. A mean of 62 for the CAPS, a standard deviation of 13.499. If we go down through, if you remember, when we compare our mean to this sample of individuals who have been involved in motor vehicle accident survivors don't have PTSD, their CAPS score is at 24.7. So essentially what we want to say is, does our sample who we have diagnosed with PTSD, is that reliably different than this reference sample of motor vehicle accident survivors who didn't have PTSD? So we're comparing our mean of 62 with a test value of 24.7. Here's our test statistic, our degrees of freedom. We see that a T of 14, obviously, clearly meeting our criteria for statistical significance. Mean difference, and then our upper lower bounds for the confidence interval around this. So what we want to do first is we want to calculate our effect size. And so here, what we do is we take our mean difference here, 37.3. Also, we take 62 and subtract it by 24.7. Gives us our difference between our sample and our test value. Divide that by the standard deviation of our sample. Remember, this is a single sample t-test, not a z-test, so we don't know the population variance. So we're going to use our sample statistic here. We divide those two, we get an effect size of 2.76. So essentially what we're saying is that our sample of motor vehicle accident survivors with PTSD are scoring about 2 3/4 of a standard deviation above this reference value for accident survivors without PTSD. So this is good. This is telling us that people who we've identified as having post-traumatic stress disorder in our sample are scoring significantly higher than individuals in our reference study who were not diagnosed with PTSD. Okay, so now what we need to do is we need to go over, and so here's our effect size. What we want to do is calculate a confidence interval around that. So we pull up our non-centrality calculator here, and what we want to do is we want to select a T because we're working with T statistics here, and over on the quantity compute we want a 95% confidence interval. So we're going to make sure that we've got T 95% confidence interval, and then all we need to do is enter our test statistics. So if we go down through, we've got our test statistic of 14.358. So enter 14.358 with the degrees of freedom of 26, obviously getting that from right here, and we go ahead and we hit compute. And so we get a lower limit for a non-centrality parameter, lower limit for the non-centrality parameter for a T of 14.358 with degrees of freedom 26. Lower bound for a non-centrality is 9.981. Upper is 18.7674. And so if we go down through, we can make note of our non-centrality parameters, upper and lower bound. Then all we need to do to get a confidence interval around this point estimate of effect is go down through and plug this into our equation here. So we've got the lower bound, 9.981, divided by the square root of our sample is 27, gives us a lower limit of 1.921. Go through, take the upper limit, 18.674. 18.674 divided by the square root of 27 gives us an upper bound for our estimate of effect of 3.59, and so we take these things through. These are upper and lower bound for our confidence interval, upper and lower bound for our effect size. So we've got an effect size of 2.76 with a lower bound of 1.92, an upper bound of 3.59. Now you notice this is a massive interval, a very large interval, so we've got, anyway, I mean, it all falls within very large effects, but we've got a lower bound of close to 2 to an upper bound of over 3.5, with our point estimate being somewhere in between here. But again, confidence intervals on our effect sizes tend to be pretty wider than confidence intervals around our mean, and so when we have very small samples, we're generally going to end up with some pretty big interval estimates. So this is how we would go through with this example and calculate a confidence interval around our point estimate of effect for this single sample t-test. Now, we can also go through, and I have you do this just to show you setting up your effect size calculator, just demonstrate how nice and easy this can be. If we go through here, and I've got this set up for a single sample test, if I enter my mean for my sample, it'll be 62. My reference value, 24.7. Okay. Variance, I have this estimated as variance. We go through and calculate the variance of my sample. So if I take 13.499 and I square that, it's going to give me a variance value of 182.223. Okay. Then go down. Sample size here is 27. My lower bound for my non-centrality parameter is 9.981. Upper bound 18.674. And if we go down through and now take a look at sort of output here, we see a t-value that was calculated through my calculator that's identical to this. Degrees of freedom identical to this, so we've just calculated our test statistic here. And then our point estimate of effect is identical to what we have up here, 2.763, and then our lower bound for our confidence interval, 1.92, upper bound 3.59, right? Everything lines up, we're good. This is nice to have this calculator set up, or this spreadsheet set up, so as you move down, as you go through working on your projects and things like that, you just have this all set up, you know it's correct, and then you can just use this to calculate things quick and easily. So that was our example of our single sample test. If we go down through and we go and pull up our independent sample test, remember the example that we're looking at here is 4 individuals, men and women, who have been involved in serious motor vehicle trauma. We're interested in this hypothetical example whether or not we have differences in marital satisfaction. So if we look here, and this is just pulled from the handout that I've given you previously, we have Lock-Wallace total. This is our marital satisfaction. We have mean for men, we have 5 men, 21 women, mean satisfaction scores and standard deviations for each group, and then our statistical test going on right here. Okay, so first thing we need to do is we need to calculate our effect size. And to get our effect size, first what we need to do is we need to calculate our standard, or our pooled variance. Okay, this is important. Remember that you want to use the same standardizer for your point estimate of effect as the variance estimate that's going into the calculation of your test statistic. So here, if we go down, we're assuming that SPSS is using a pooled variance estimate to calculate this test statistic, so we're going to do the same. This is just using our pooled variance formula, so we've got sample 1 minus 1 times the variance of our first group, 1 minus the sample size for a second group, the variance of the second group, sample size 1, sample size 2 minus 2, gives us a pooled variance of 650.426, and we take the square root of that, gives us a pooled standard deviation of 25.503. Okay, remember, always work with the variance first, and then once you've got the variance, move down, and you can take the square of that, or the square root of that, to get your variant, or your pooled standard deviation. Okay, so we've got our pooled variance, got our pooled standard deviation. Going to calculate a Hedges G. I have it as D here, but essentially taking the difference between our two groups, right? So we're going to take 108.874 minus 80.23, gives us a difference of 28.644. Divide that by our pooled standard deviation, gives us an effect size of 1.123. Okay, so there we've got our point estimate of effect. Now what we need to do is we need to get our non-centrality, upper and lower limit for our non-centrality parameter. So if we go down through, this is all set up already. We want to go down through, we take a look. Say our test statistic is 2.257. I wouldn't worry about the negative there. It's sort of arbitrary. It's not going to make a difference. You're going to still get the same upper and lower limits. Degrees of freedom 24 for this test. So we've entered our test statistic. We've entered our degrees of freedom. Go ahead and hit compute. 95% confidence interval for this is going to give us a lower bound for a non-centrality parameter of 0.175, upper bound of 4.296. So we go down through, note that. So we've got our upper and lower bound for a non-centrality parameter, and then once we've got that, then it's easy. We go down through and plug both our upper and lower bound into this formula. So we've got 1.75, which is our lower bound, times the square root of 1 over 5 plus 1 over 21. Make sure you're using sample sizes here and not degrees of freedom. That's easy to get turned around. Multiply that together. Excuse me. Get a lower bound for our effect size of 0.087. Do the same thing for the upper bound. Take 4.296, multiply that by the square root of 1 over 5 plus 1 over 21, gives us an upper bound of 2.138, which gives us our confidence interval. So our point estimate of 1.123 with a confidence interval, plausible range of affected in the population, anywhere from something that's incredibly small, about almost a tenth of a standard deviation, anywhere to 2 full standard deviations, over 2 full standard deviations. Again, we've got a very small sample for this example, resulting in a very large interval estimate for our effect. So even though we might be pretty excited about this effect here, if we were interpreting this in terms of someone else's research, we would say, well, that's all well and good, but in actual fact, we would expect probably the range of plausible values for the effect in the population based on this confidence interval to be quite large. Okay. Again, just demonstrating how these calculators can be effective. Again, if we go 80.23 and then 108.874, we'll call it. Okay, standard deviation for my men, 30.366. For the women, 24.415. And so you got the variances already calculated automatically here. I got a sample of 5 for the men, 21 for the women. Non-centrality parameter, 0.175. For the lower bound, 4.296 for the upper bound. And we can go down through and we can take a look and see that this has all been calculated for us, right? Our test statistic, same thing as what we've got in SPSS, so that makes us happy. Our pooled standard deviation is what I had calculated up here. Same thing with pooled variance, that all matches up, so this is nice. This is just a double check. Degrees of freedom, all the same. So everything that's being calculated in our Excel spreadsheet is identical to what we have here. We've got our Hedges G, 1.123. 1.123 adds up perfectly. Our lower bound, 0.087, rounds to 2.09, upper 2.13, round up to 2.14. And so we see that everything is on the money, and so this is just a nice way to go through and plug this stuff in and have it calculated for you. Once you've got it put together, you've developed it, you know that everything is correct, lock this down so you can't accidentally screw things up, and then just use this as a nice tool. You'll also notice that in this case, we've got a low, pretty small sample, and so a hedge's unbiased G might actually be a better point estimate of effect. However, there's a correction here, and we can't calculate a confidence interval on unbiased G. We would just have to use G with a pooled standard deviation here. So depending on what you're doing, you could report both, but if you really want to calculate a point or a confidence interval around your estimate of effect, you should probably be using G, just a standard G as your point estimate. All right, last example, going through with our paired sample. Right. Remember that this is, in this hypothetical example, we have people who have been involved in some inpatient treatment, and we're looking at changes in interpersonal style. We want to see if we see a difference or a reduction in sort of this cold, distant interpersonal style from pre-treatment to post-treatment. So first thing we need to do is calculate our effect size. This is easy. We've got the mean of our difference score, or if we just take 4.26 and subtract 2.58, it gives us the same number. Here, SPSS has calculated the difference of 1.684, and remember we're going to divide this by the standard deviation of the difference scores. Now, this is important because, again, particularly for your paired sample test, if you don't calculate your point estimate using the standard deviation of the difference scores, which is the same variance estimate that goes in the calculation of your test statistic, you're going to get a confidence interval that doesn't contain your point estimate. And anytime that happens, you know you've gotten turned around somewhere. So, but if we take the mean of the difference scores, or time 1 minus time 2, divide it by the standard deviation of the different scores, we get a point estimate for our effect of 0.68. So about 7/10 of a standard deviation reduction from pre-treatment to post-treatment. Okay. Then if we want to go through, next thing we need to do is calculate our bounds for our non-centrality parameter. So in this case, we've got a t-statistic of 2.968. So we enter 2.968. Our degrees of freedom are 18 degrees of freedom. Compute, and so we've got a lower bound for our non-centrality parameter of 0.751, upper 5.118. So we go through, mark that down, and then just as we did before, taking these bounds, plugging it into this formula here to get our upper and lower bounds for our effect size. So lower bound 0.751 divided by the square root of your sample size. Again, make sure this is your sample size, not your degrees of freedom. And you get a lower estimate of 0.172. Take the upper bound, 5.118. Divide that by the square root of your sample size, get an upper bound of 1.74. Ends up with a confidence interval around your effect. So point estimate, about 7/10 of a standard deviation reduction, but we would expect this effect in the population to be anywhere from a little under 2/10 of a standard deviation to over a full standard deviation reduction. Okay, and again, modeling your calculator spreadsheet here, we go through and we enter 4.26 for time 1, time 2, 2.58, standard deviation at time 1, 3.649, standard deviation at time 2, 3.717. So we got the variance calculated, standard deviation of the difference score, 2.473. And correlation, we don't have that here, so we can go ahead and delete that. And then my sample size is 19. Lower bound for my non-centrality parameter is 0.751. Upper 5.118. And if we go down through and take a look, now we've got a little bit of a rounding error here. We got SPSS calculated this. Our mean difference is 1.684 versus 1.68. which is fine. But we ended up with our effect size using our difference score of 0.68, so that's looking pretty good. Our lower bound 0.17, upper bound 1.17, so everything's looking good. Now this is another thing. If you go through, I also have, in addition to standardizing my effect using the standard deviation of the difference scores, also here we've got a d-average and our Glasses delta here. Now this is one of these cases. Remember, our concern with standardizing our effect size using the standard deviation of the difference scores is that standard deviation of our difference scores is often lower than the standard deviation of our scores at time 1 or time 2. This is one of these cases where it looks like we have some noticeable sort of increase in our effect size. If I were to take the average of the variances and square that and use that as my standardizer, I would get an effect size of 0.46 versus 0.68, right? Same thing with Glasses delta. If I take a standard deviation at baseline and use that as my standardizer for my effect, I get an effect size of about 0.46 versus 0.68, right? And if you see standard deviation at time 1, standard deviation at time 2, both of these estimates of variability noticeably larger than the standard deviation of the difference scores. And so something you need to consider if you want to calculate a confidence interval around a paired sample effect, this is the effect size that you have to use. Okay. However, recognizing that in some cases this will be inflated relative to if you use d-average or Glasses delta, and so just recognizing that that's going on, is that a problem, and maybe you want to report maybe 2 metrics of effect and describe kind of what's going on with this. But everything's working out good here, so we've got our calculator set up well. This is looking pretty good, and that takes us through our single sample test, our independent sample test, and our pair sample t-test. So hopefully this helps out, but if you have questions working through this set, make sure to let me know. All right, thanks.